Hello, my name is Jeff Wagner, and for the next little while we'll be taking a look at Houdini 16 geometry workflows. We've changed an awful lot going from Houdini 15 to Houdini 16, changing a tremendous amount of the SOPs that we use, and it really does change the way in which you use Houdini. I think the biggest topics that we need to cover, going from previous versions of Houdini to Houdini 16, are the fact that the point SOP has now been relegated to the back scenes. It hasn't been fully deprecated yet, in that it hasn't been op hidden, and it's the old point SOP. So we have a new SOP called attribute expression, which replaces a lot of the point SOP. We also have a vertex SOP, which is deprecated or hidden, and we're basically wrapping that all up in that new attribute SOP, which we're going to be taking a look at. We also have the copy SOP, deprecated. Not deprecated in terms of hidden yet, it's still available, but we call it copy stamp from the tab menu, as well as the group SOP. It has been deprecated and replaced with several new group operators. And there's a whole bunch of other operators. I think some of them that are sort of hitting the back road is the extrude SOP. It is still available for you. There's still one thing that you can do that may or may not be able to done with the new poly extrude SOP. And the material network has been deprecated in favor of shops. We won't be looking at that today, but we will be focusing on the point, the copy, and the group especially, because those are the three cornerstone nodes that a lot of us old school Houdini users have been using for a long time. Before I go any further though, I definitely want to explore a little bit more of the housekeeping side of things. When I get a new release, I use a pretty interesting technique where I can, for myself, find out which operators are new, which ones are not. And the whole process involves, so that means I can get my own list and I can see what SOPs have been deprecated for myself. And it's really straightforward, and it's a nice exploration of using diffing. And diffing is becoming a very powerful thing inside of Houdini 16, because we also added the ability to save a scene file as text, as well as saving digital assets as text. And then you can manage those scene files and digital assets with proper version control, and you can also do diffing against them to see what has changed and do proper management of those tools in your asset management system. And I just don't think that is in the purvey of system administrators. I do believe that TDs who have a tremendous amount of assets in play also should know how to do diffing and themselves, just to do really quick little things. And it's so easy and it's so accessible inside of Houdini. So the first thing we're going to do is fire up Houdini. The commands we're going to be looking at is the Houdini text port using hscript. And we're going to be using a cd command, which is a shell thing, opadd, which is to add operators. And we're going to be using this redirect symbol. So opadd will return to us a list of all the operators in the scene file. What makes the redirect really interesting is that we can direct the output from the opadd command, which just gives us a list of all the nodes that we've added, and you can return that to within a specific directory. And you can put that into a text file off of disk. And by using the hscript command opadd while you're in SOPs, you can get the entire list of all the SOPs, and then we can take a look at Houdini 15 SOP list, Houdini 16 SOP list, and then do a diff between the two. And for that, we're going to be using a diff application. And for that, we're going to be using beyond compare. And so in the step 2, we have both 15.5 and 16 on disk, and then we're going to use our favorite diff application. As I said, we're going to take a look at beyond compare. And it comes highly recommended from the user base. And using it in myself, it actually is very good. It does what it's supposed to do. Gets you, it's a development type toolkit that allows you to see differences between two different text files code. And we're going to be using it to take a look at the two different lists of SOPs. And you can get that software from scootersoftware.com, and so your screen file should look somewhat similar to this. So let me go down here. So beyond compare. So let's get started. So now I'm in Houdini 16, And I just want to dump a list of the various SOPs that are available to us when we hit the tab key, or when we type up add, or however we wish to add an operator. I am using the technical desktop, which gives me access to the Python shell as well as a text port and the bottom stow bar. And in the text port, let's raise this a bit, and I can type in the command, as we said before, op-add. If we just type in the command, it's going to give us a long list of the available operators in our current directory. So we can also type in help. It gives us a list of all the various commands that are available inside of Houdini. And commands allow us to reconfigure the interface, list operators, connect with remote devices, basically everything that you can do with commands inside of Houdini. So help op-add gives us a listing, and if we scroll up to the top of the help, we'll see that it says with no arguments, the command prints a list of the operators. So let's see if that actually is true. So we just type in op-add as we saw before in the current directory. So we need to go into /obj, so cd/obj, which allows us to go into the obj network. Again, we can do a listing with using ls. We can see that there's no operators available to us. And Houdini really is a path system. And we need to get into that /sop directory. We need to get into a geometry directory inside of our object. And the only way we can do that is to actually add an object. So clicking the cursor in the viewport, tab, sphere. And that adds a sphere, or any piece of geometry, anywhere we can actually go into SOPs. And we can actually, in text port, type in CD, and then grab our sphere object and drag and drop it. Just drag and drop it right into the text port and hit that and hit enter. And click in the viewport, in the text port, then hit enter. And now we're actually inside of the sphere object context. And now we can type on op-add, and it gives us an entire listing of all the available operators to us. Same as if we were to hit the tab menu in the network editor. All those operators will be listed in here. So the idea here is we want to dump this to disk. And we can type in op-add, and we can use the redirect command, which is the left arrow. And we're going to save it to $temp, TEMP /, and let's give it a name called h16.0 underbar sops.txt, because we want to write out a text file. Extensions are important inside of Houdini. So when we hit enter, that actually gives us a long listing of the files. So let's see if we can find these files. So I'm on Windows. On Linux, you just open up a shell and you just type in cd $temp with the Houdini environment. It gets you into the right location. On Windows and the Mac, it's Mac also has shells, but chances are most users won't be using them. So we're going to be needing to use a file browser. So in Windows, I put up a file browser, and we want a CD to this directory called temp. Temp isn't one of those default hidden directories inside of Windows. So first thing we need to do is there's another shell command inside of Houdini. When you launch Houdini, it inherits all the system environment variables, including temp and temp. So we can echo $temp. So we can expand any variable that Houdini inherits, including system variables. And if you're working in a company that has a lot of variables set, you can actually inspect them inside of Houdini as well. If you harden the variable inside of Houdini and you call it, you write it, it'll actually get saved with the scene file as well. But for most times you want Houdini to inherit the system environment variable, which is the default behavior. We have this path here, so I'm going to take this and Control-C it, and then go to my File Explorer. And right in the top bar, you can actually hit Control-V. And even though they're forward slashes, these days Windows is very compliant. It takes you to the right spot. The reason why you won't normally see this is because app data is a hidden directory inside of Windows. And you can see that a $temp actually expands into the system temp, Houdini temp. So what we want to do is go up one directory. And we can drag and drop this over to our quick access. So that means it becomes available to us at any point in time. So we can just press on there. And we can see that I previously launched Houdini 15.5 and dumped out the same listing of SOPs as I did inside of Houdini 16. So with our two files up and available, let's actually fire up Beyond Compare. So in Windows, I always like doing this, doing the type on the Mac and as well. And here's Beyond Compare, which I downloaded. and installed. And you can take your two text files, drag and drop them, and it gives you a listing of all the operators. We can take a look at all the various changes in these two files and compare them, or we can just see what's different. And here, now you can quickly have a look and see which operators are new and which ones are old. You can see that a tremendous amount of operators inside of Houdini 16 were added. Very easy to see all the height field operators that we added. So whenever you're downloading a new build, give this a go. It certainly does give you a really clear look as to what operators are new. And then you can go to the forums or contact support. Well, there's this one operator, try to use in Houdini. You may or may not know how it works. The documentation may or may not be in place yet, especially if you're on beta, testing beta versions of the software. It really opens up a lot of the interest that you're in there. What makes this more important is later on in another video, we're going to have a look at diffing between two different assets. But now you are in control. For instance, there's solid fracture, solidify. These are all having to do with TET mesh and a lot of the work that we've done on the FEM side of things and muscles and all of that. Just tissue solver again relative to muscles. A lot of stuff right here. No need to go to a list. You're in control. So out of that long list of new operators between Houdini 15 to Houdini 16, I went and grabbed a bunch of the operators that would be interest to those who are using SOPs to do procedural modeling and procedural creation of data, whether for film, games, commercials, whatever. And it's quite a long list of new operators. There's a couple things that we really need to cover, though, is those key operators that were deprecated, including the copy operator, which has been replaced by copy to points and copy and transform. And those two together form what we had in the old copy SOP with no stamping. And we'll take a look at how to address that. We also have a whole bunch of group operators that are used to address the issues that we had with the old group SOP. And it's quite peculiar, that the old group SOP actually didn't have a group parameter field, which is actually addressed with group expression. So we'll take a look at that unique operator as well. Intersect analysis, if we have time, definitely have a look at those. And a few of the other options in there. VDB grids, again, addressed in another, that's definitely worth covering in a completely different video. Lots of improvements with VDB since we went on to the version 3 and above. So without ado, let's actually have a look at the very first operator we want to take a look at, which is the point node. So now we're back inside of Houdini, and let's stow this up. Let's recall this object, just rename this object. We're just going to call it point examples and dive inside of it. So we have a basic sphere. Let's do some work on it. If we have type in point, you can see that we have point old, which is the old point SOP. And let's put down a new point SOP. And the first thing I want to do is put that down. Let's actually add the point old as well, just to have a comparison between the two. We notice that right off the bat, the new point SOP is actually called attribute expression. And it actually allows us to work with detail, primitive points, and vertex type data. Whereas the old point SOP, we actually had the vertex SOP as well. And vertexes has been replaced with attribute expression. And I actually think this one, vertex old, there we go. So that's still available to us as well. So with that one operator, we can do both what the point SOP was able to do and what the vertex SOP was able to do. And if you guys remember, the old school guys, if you remember, normals are always something that you gotta worry about in the old system, where the point attribute type normals or the vertex attribute type normals. And there's no mystery that Houdini is, because of the industry, games, and a lot of assets that we bring in, all the attributes, like for instance, UVs and normals will be vertex type attributes. It makes sense to use the attribute expression. A couple other things that we have at the point SOP, for instance, the old position at P. I'm still old school. I still like $TX, $TY, $TZ inside of here. And you can do TY +2. And we can move our geometry up 2 units. So what's the equivalent in the new point SOP? In the new point SOP, we actually have some really nice options available to us. If we press on the arrow button to the right of the parameter, we have pass-through, which is called self. And there's a couple things that we need to know about with the new attribute expression SOP is that there's self and then value. So we can actually go something like this, self plus value. And what this means is inherit the attribute point position P and then just add whatever is in value. So if I hover over value, you can see that it's that's how we access this particular parameter. So if we then put in here 2, we now get the same thing. So much easier to access the basic stuff. And the most important part is it's also compile friendly. So what I'm going to do now is I'm going to hit the D key inside of the network, D for dog, or I can actually open up it from the viewport, but I'm going to open it up in here. And by default, Houdini has this option called compatible SOP badge, and it's hidden by default. I'd say if you're a TD and your profession is using Houdini, show it. I'd definitely turn it on normal. For casual users, new users, no need. But we are concerned about workflow, performance, whether or not these assets are going to be play inside of Engine on a massive farm if we're on games. Or if we're on film, we don't want systems getting back to us saying, you know, your assets are running really slowly, generating data to render. So we have some techniques that allow us to enhance performance, one of them being compile blocks. And compile blocks work on nodes that have been verbified. We'll take a look at that in a minute. But for now, nodes that you see that have this compile badge, which is a gear with a slash through it, mean that they no longer play in the new compile type workflows. In other words, they won't be able to be threaded inside of these compile blocks. They're still usable. If you still need to follow tutorials that are done previously, absolutely do that. But beware that the changes are afoot, and we have the new attribute expression. So in the next couple minutes, let's take a look at some options that we have. We already saw how we can basically do the old ty plus 2 just by typing in self plus value. And that's the barrier for entry to the attribute expression, is literally knowing that self inherits the attribute and then value determines the new value. So what happens if we get rid of self? So I'm going to copy and paste this node. And so the next version, always copy paste, guys. If you get something that works and you want to make a change, copy and paste the node. As a matter of fact, we don't even have to use control. We just can hold down the alt key and just drag a new copy. Just holding down the alt key. Let me do that again. Hold down the alt key, select your node and just drag it off. It drags a copy. So now I'm going to move my display flag in here. Let's take a look if we just get rid of the self. We just go to value. It all gets plowed down to 0. The reason why, or at the units too, so if I turn my points on, you can see that everything is 2 units high. So value is basically saying I'm taking P, getting rid of everything, and then just using the value. Again, it's self. So it's pretty evident as to what's happening here. So this works in all the geometry in turn. We have a few presets available to us. There's constant value, which we just took a look at, which is what we had. Then we have multiply by constant value, so self times value. So if we want to scale the geometry up, right now we're scaling it in 2, but if we just want to basically scale the geometry by 1, we now have a scale, so a non-proportionate scale. The only thing I do not like about this is there's no management of the origin. So that means if we move the sphere up a few units and then did that down here, it's going to be scaling. Actually is scaling around the, there we go, it is scaling around the origin. So, and there is no control over the origin for that. So, yep, buyer beware, as always. Control middle mouse button, if you guys know that, I hold down the control key and use the middle mouse tap on parameters to reset the defaults all the time. Let's take a look at some other options in here. Add a constant value. That's where we were at before. We say self plus value. So if you forget or you need to be reminded about the various options, you can always go and add constant value. Basically gives you everything you want. Random. So now we're in the realm of Vex and Vex expression writing. Over the last couple of, I think about 2 releases ago, we did port the majority of the HScript commands over to vex. So we actually have a rich library of expanded vex functions. So if you're trying to move from the old point SOP to the new attribute expression, the majority of the expressions are available to us with a lot of really handy variants. And let's take a look at one of those variants. There's a few other options of random flatten vector allows us to flatten. And this one's introducing another. So these options in here are meant as reminders or to teach us how to do the standard things inside of the attribute expression. In this case, we're actually using a set function. And the way I look at set, let's add a couple spaces in here to pad this out so it reads a little bit more interesting. You can treat this as though those were the three inputs into the point SOP. The old point SOP has X, Y, and Z. And if we're overriding position, you can think of that as X, Y, and Z. But the benefit that this is all working with vectors. And we can see here that by using .x, we can actually index into the first, second, or third component of the point position, which is defined up here by self. Self.x, 0 self.z. So this allows us to flatten. Of course, if we put a 1 in here and hit enter, you can see that we're moving it up one position. Let's set that back to 0. So the set function is very important. It allows us to set the value as, in a very proper way with variables inside of it. Another example is subtract center of first input. And this one's pretty cool because what it will do is no matter where our sphere is located in space, it's going to put it at the origin. So temporarily, I have Houdini set the default, which is work on the current selected node, meanwhile displaying the result of the network. So that the yellow halo. So if I hit the T key, move my up, you can see here that no matter where I move my sphere, it's going to be centered around the origin. And let me put the template flag on the sphere as well, so we can actually see that. Now let's take a look at how the attribute expression handles normals. So we're going to put down another in here tab point. Add another new node, wire it up. And in this one, we're now going to take the position, but we're going to say, we're going to put not self. We're going to do self, which means we want to take the incoming point position and add to it the normals at n. Very common to do in the old point SOP, and here's how you actually do it in the new world. So self plus at n. Heck of a lot easier than using tx plus $nx, and sure enough you could put times 0.2 in there, and then you can scale that sphere up. You can see with the selected on there we can do that. So in the new point we can do the same thing, but we just have to know one thing. So I'm going to leave that in there. I'm going to alt drag another copy of this, and here we're now going to go use the set function. So let's use self, and I'm going to copy that, Control C, and type in set. And in here we can put in, let's first of all do self. We want to inherit the point position plus set. And what we can do in here now is inside the set function we can put in 0, 0, 0 and make sure that all works, which it does. And now we can see that we are starting off with, we can actually change that to 1, and we can move it to 1. So we got it working. But it's not going to work that way. So what we want to do is break out set, and let's delete that. And now we're in complete control. So basically we're just taking, and we can actually do the same thing by doing self.x and self.y and then self.z. Z, as Canadians like to say. And so now we're back to where we were before. We can add that offset now per component. So it's just like we're working in the old point SOP, except now that we're working on vectors, so we get that efficiency of vex threading for free when we got more than 1,000 points that we're processing. So and this is just how we work at it. So self plus x plus let's put a 1 in there and Control Enter, and now you can see we move it in 1. So we have a lot of control over what we're doing. So let's add the normal component. So add n dot x, and let's put times let's put in 0.2 for now. And I'm going to grab the same, I'm going to do the same thing here, plus at n dot y, times 0.1, and then finally over here, self z, I have to put the plus in there, sorry. And in self z, let's just at least take a look at what we've got here now. So we can actually add add the normal to our geometry in any different way that we want. And self.z, let's add n.z, and we're going to multiply it by a very small 0.1. So order of operations are in play here. If you want to formalize this is fairly straightforward to understand. There's going to be no ambiguity whatsoever. So we know that the order of operations states that multiplication, division happen first, then addition, subtraction happen after that. So in this particular expression right here, that evaluates first and that evaluates. So nothing's changed with regards to the old school point operator. So if you're trying to follow along, $nx is now at n.x, and self-x is just how we access the incoming value, and whatever we have this set to is what we're working on. So let's alt drag this again. This time we want to take a look at what it looks like to actually affect the normals. So I'm going to go this, and I'm just going to go in here just to let's put in here add a constant value. So we're taking self and value. And in this case, we're going to actually now start affecting the normals themselves. So middle mouse on the sphere gives us just the point attributes. And then middle mouse on the point expression gives us normal and point attributes. So this is actually how you create normals. If you wanted to not use the normal SOP, we could just use self. And this would actually build us the normals for us. Time to look at the spreadsheet. Again, I'm in the technical desktop, gives me access to this really easily. If not, you can right mouse on the node and just go into spreadsheet as well. And this actually creates a pinned spreadsheet on that specific operator if you want. And we can see that we actually have, looks like varying normals. Good. If they want to make sense of them, turn on the viewport. Then we can see that we certainly have normals now created for us. What's really cool is Houdini will still show you the normals. In this case, if you're not showing any normals in 16, it's kind of interesting that the normals are now defaulting to vertex normals. So you actually see the vertex normals on your geometry. So on bypass the node, we can actually see we've hardened point normals. And those point normals, we can do whatever we want with them. Many times we use that to birth a lot of particles. So we can do self plus value. And this is where this thing really starts to kick beyond what the old point SOP was. Finagling normals in the old point SOP was But now self plus value, we can actually add values. And there you go, bang. And if you want so that means now if you were to birth particles from this, it's really easy to see how those particles would distribute. And we can actually self plus value, and then you can add a second one and do multiply by the value to get it to go. So let's do that. Let's alt drag a copy here and freewheeling here a bit so we can actually self times value. And so 2 in combination will give you some really interesting things. So you can actually take the normals and you can flare them out. Let's get that to 0. So you can take the incoming normals, and we have to set that to 1 by 1, by the way, because we're now multiplying. So multiplying by 0 gives you 0, obviously. And now you can comb the normals however it is that you want and create really just a couple point operators. Now you can create some really cool effects. Very artist friendly to work with. I just accidentally locked the node. And so you can use these operators in combination. Of course, you can use a point wrangle to do all of this stuff as well. But the whole idea behind the point expression is teaching basic concepts, and that's where the point SOP was really good at. And I'd argue that the attribute expression is right there as well once you understand the basics of how that it works. Another thing we can do with the new attribute expression is munge around with some colors. So let's drag and drop this guy. We're using the Alt key, create a new copy, and instead of picking on the points this time, we're going to pick on primitives. And let's get rid of this expression. And some of the attributes that we can add to primitives are color. Normal, believe it or not, does not make sense. Everybody says, how can I change my primitive normals? The answer is primitive normals are intrinsic to the primitive and the vertex winding. You cannot edit a primitive normal. You can inherit them onto points or create a new attribute, inherit the primitive normal, then affect it that way. But the primitive normal is one of those intrinsic properties that is read-only. Having said that, we can do the color. And for that, we can now primitive override the color, and now we can change the color of our primitives. Really simple. We can use random, so we can say random scale of values. And now we can, we're doing a random called lmnum. And this is the third part of the attribute expression that we need to get used to. It's lmnum. So if we want to do random per point, random per primitive, random per vertex, lmnum is how you access the current number being evaluated. And in this case, we're doing, for the lmnum just happens to be the primitive number. So now we're randomizing each primitive based on that color. And what's really nice about this is we can actually tint that with a value as well. So if we want to have a spectrum of color, just set that to 1 by 1 by 1. And we now have a grayscale into the value. The reason why is float is returning a single value into value. But anyway, that's how you can get nice random values into the primitive. So another thing that we can do, instead of doing primitive colors, let's do an alt drag on top of that. We can create custom attributes. So we can create a custom attribute under primitive. Let's do custom, and you can see in here my prim attribute. And my primatter, we can set it to whatever it is that we want. So right now it's set to a type of a color. We can choose the type. Let's add a float. And in the spreadsheet, as we're following along, if we take a look at primitive, you can see there's my attribute, and we can basically do a random value into there. If we want to just create a random value, we can do that very easily. And so it's rand lmnum. And let's get rid of that back bracket. And there we go. So now we got just a whole bunch of random numbers set to my attribute prim. If you want to use this later on, great. We can also use my primatter to do all kinds of things. Yeah, it's just a way of adding custom attributes. Let's alt drag this again. And final look, attribute expression going into detail attributes. Detail attributes I like to use as take a look at the detail attribute as a way of just creating an attribute that's constant across the entire geometry. My detail at, and we can set that to whatever we want. In this case, lmnum means 1. It's going to return 0 regardless because there's only 1. So in this case, we can just set this to a value. So we have a detail attribute. Let's make another copy of this. And now we want to take a look at adding strings, whether it's detail, primitives, polygons, or vertices. Strings are handled the same way. And let's set this to string. They are a little bit tricky. So if we did want this expression to evaluate as a string, first of all, we need to use double quotes. Regardless of whatever value you put inside of here, they have to have double quotes on them. Hit enter. And it literally puts the string into the random function. Maybe you want to evaluate this at a later time in a different location. That's now very robustly handled. And I have to argue that another problem that we had with the point SOPs, if we go all the way over to here, is if we wanted to raise up this expression, say encapsulate the point SOP inside of a digital asset, and we wanted to raise this up, we'd actually have to use CHS raw or or a particular variant of CHS how we wanted this thing to evaluate, and it was just a rat's nest of trouble. You could get it to go, but with the new attribute expression, it's just a parameter value. You raise it to the top, and you can give the exact same experience to the user whether or not they're in the attribute expression or not. So it simplifies asset generation tremendously. Sound like a salesman trying to pitch this thing, but it really is very useful. If we want to evaluate this in turn, if you're familiar with it, it's just the simple back quotes. So we can now evaluate that as well. And if we wanted to add text to that, just like in other languages like Python, you add strings together with the add operator, which is a plus. And in here, I can just type in foo, for instance, so we can put whatever text we want in there. And it says plus foo, so let's get rid of the plus. We don't even have to add it. It's a literal string. What am I doing? So underbar. And now you can, for instance, if you have to do piece element on using a name attribute, trivial. I mean, these sorts of things that even in vex wrangling would be a little bit difficult are very trivial inside of the new attribute expression. So again, detail attribute. And what's nice about this is we can add it to primitives as well. And maybe here we want to do, let's, instead of, now we're doing lmnum, so that means we basically, whatever primitive we have, And then finally, if we go to points, you get the idea. When we go to points, you can see that it's evaluating. So it's still evaluating the same value. So I take it that rand elem num is not evaluating. It's a string. So there are some, leave it for detail. That's what I'd probably say. Detail, for instance, you want to encode some file names for some path directories for file names or whatever you can put inside of that. And I think that's enough on attribute expression. So to conclude on attribute expression, it does replace the point SOP. It's compile friendly. It offers common attribute operations on all the incoming geometry, just like we had with the point SOP. I would argue even easier to access. And it opens up the entire scope to point vertex attribute, primitive, and detail attributes. And it has all the common operations. If you want to affect normals, easy to do that. If you want to add color, easy to do that. If you want to add a custom attribute, initialize it, and move forward, a great way for new and existing users to just quickly get some stuff in there. If you just want to create a constant value, this is your weapon of choice. I would say it's even more directly accessible than a Wrangler. So what I'm going to move on to next is, so we want to take a look at for each block improvements as relates to the copy SOP. So let's go back to our existing Houdini scene. And in that Houdini scene, let's stow our detail view. And let's start from scratch. Let's go up, turn this guy off, and let's add a new piece of geometry. This time it's going to be a box and dive inside of it. And what we want to do is do some work on this box after we copy it to a grid. I'm going to go to the viewport, upper right hand side of the viewport. We have a tool and option. I always do create in context. That means if I create a new grid, it'll actually build it inside of this specific object. So I'm going to enable that. So create in context should be set to create in context. And now I'm just going to tab grid. By the way, if you add a grid and you go back up to the object level 2 objects, you forgot to do that. And so now I got a grid. What's nice about this workflow is it adds, instead of a template, we actually have the selectable template flag as well, which actually allows us to work on independent leaves of nodes inside of SOPs, if you were unaware of that. If you don't want to do that, you can just turn that off as well, which we are going to do. So you have to click it on twice, by the way, first to turn it into a regular template and then finally to turn it off. It's one of those two-way type toggles, or three-way off template and selected template. So now we got our grid, and with our grid selected, let's tab in the viewport scatter. And it wants, so I just tap, it wants me to select all the primitives. I just tap N for all and hit enter. And we're one of those, it's group blank means everything, not star. So it's kind of interesting how they do that. But anyway, scatter points. And we're going to put down the copy to points. And this opens up a whole can of worms, because the old copy SOP, which is still there, I mean, actually it has been, there's the old copy stamp right there. And old copy stamp, if we wanted to do work, we'd have to use the stamp variable. So we're going to have a look as to how this actually works. So now we want to wire up the copy to points properly. And let's take a look at a simple example of where we want to do some work on the box, in this case subdivide it. It's important to note that the copy to points inherits all the attributes that the copy SOP did and does all the same things. For instance, in the scatter, we can set output attributes into output p-scale. And if we go back to the options of the scale, we can change the override count. We can see that the p-scale is set to the relative radius between the two blocks. And as well, we can add all kinds of attributes. And let's put down the attribute expression, which we took a look at earlier. And let's add custom. And this time, let's call it scale. If you go to the help docs, it'll tell you what attributes work with the copy and copy to points. And we want to set this to value. And because it's a scale, we should at least start off with 1 by 1 by 1. So 1, tab, 1. So now we got a scale. And the nice thing about this is you can scale it on the various axes individually. So in the copy to points, let's take a look at the box. Let's put down a subdivide. And if the subdivide below the box, let's see what some valid options are. Many times subdivide does rounding. In some procedural systems, we want to just add detail to the various faces. So for that, we can turn on override crease weight, double click on the depth parameter, and then drag and drop that on top of the crease weight. We can say relative channel reference, and that creates a relationship between the two parameters. Note that for newer users, we don't adhere by the convention where the label name equals the actual name of the parameter. We break for various reasons. When I build my own assets, I make sure that I try and create the parameter name the same as the label. It's just one of my own rules. Just be wary of that. So now we're going to have a look at some values for the subdivide that make sense. 0 makes sense, 1, 2, and then 3. So 0, 1, 2, 3, let's say that's a good range. So between, and let's turn caps off, between 0 and 3, just to make sure that we have a nice reminder all the time of what it is we're doing. So as we can see with the copy to points, in order to get stamping functionality, we need to lean on a for each block now. So if we hit the tab key, we type in for each. And this really hasn't changed since Houdini 15 and 15.5 when we introduced this functionality. One of my peeves is that we have both nodes selected, so I'm always deselecting. And I will forget as we go forward, and I'll move both nodes accidentally. Now the question is, I have an iterator, and with the copy to points, it makes sense where what I want to iterate on. And I want to iterate on each one of these points flowing into the copy of the points. And then counting for each point, I want to create a condition with an expression that allows me to set a unique value for subdivide for every point using a random function. So first, copy to points is really easy to wire this block begin. And the end is probably where I want the display flag or the result to flow out to, which will be the output of the copy to points. And now I move my display flag onto here. And you can see that there are two errors. And they have to do with the initial state that these nodes are in. We do have to choose an initial state when we design these tools. And the initial state we designed these for is to process pieces, let's say from an assembly coming out of, packed primitives coming out of a rigid body system. Or we're trying to process or iterate over an Alembic archive or any sort of packed archive where there's going to be a relevant name attribute. It's not the case here, so let's disable that. Secondly, the piece elements are iterating over primitives. We're actually iterating over points, so that's what we're going to change this to points. And now the errors are cleared. But we need to incorporate the subdivide and work on each iteration of this for each loop. For that, we have to lean on another block begin, and we're going to create a new meta import node. Again, both nodes are selected, so I'm always deselecting. And then moving this node down here. And this one is set, so this first one is set to fetch piece or point. And if we take a look at the for each block, that is what it's iterating over. And this one is going to be our counter. And let's call this iteration. And by default, when it's set to fetch metadata, it's creating, and we give you a bit of a breadcrumb here, detail attributes, iteration, numeration, value. So the expectation is you select this node, and then you go to the detail attribute in the spreadsheet. And here we can see we have iteration 31 of 32 iterations. So iteration counts from 0. A number of iterations obviously is counting from 1. That's the disparity there. We can go to the for each block. Let's go back to iteration and remember that we've pinned the spreadsheet down to the iteration. And now we're going to go to the for each block and we're going to turn on single pass. And you can see here you can iterate over each individual pass. And we can see here how the detail's updating, iteration of 1. So single pass 3, iteration 3, iterations 1. So that means as we inspect this network, it'll all remain valid. So now we need to reference that iteration detail attribute with a detail function. And we're going to do that on the subdivide. So selecting the subdivide, under depth, we can put an expression in here. And I'm purposely not going to include this in the for each block. So you'll see it fail. So, but anyway, let's see what we can do here, or at least it'll just default to a value. So I'm going to put in here detail. Let's one step at a time. Detail function, and the way the detail function goes is if I hover over the help, all this function does is points at a particular SOP, not myself, but any other SOP upstream of my evaluation. And then you can say, what's the detail attribute? So the operator is the first argument. The second argument is the name of the attribute that we wish to pick up, which is iteration. The third one is 0, 1, 2, 3, 4, which is the element within that attribute that we want to pick up in case it's an array type or a vector type. So let's point it at our operator. Colon, .. iteration. We can see that the nice list is giving us. So let's remove the trailing slash, double quote. Now we need to put down the name of the attribute, which is in quotes again, iteration. And then finally, the last value is 0 because it's a single float. And we do that, and we get a depth of 0. And that's because it's evaluating to a constant. We need to wrap this up inside of the for each block. In Houdini 16, we added a new option. So I'm going to select the blocks begin. And under create meta import node, we're going to press that. Again, we have 2 selected. I'm going to deselect them both and select the one I want. And I'm going to drag and drop that above my subdivide. So I'm now bringing the subdivide inside of the for each block. So now it will iterate along with the copy to points. So in the for each block, I'm going to change it from fetch metadata though to a new input which we added in 16 fetch input. So now everything is going fine. So I'm going to go to the for each, turn off the single pass, and it's now going to evaluate. It's doing the subdivisions, and I'm going to escape this really quickly because I did the number one failure here, is that I didn't bound my subdivide. That means I could have had a subdivision level that was huge, so please don't do that. So what we're going to do in here is put a random function around this immediately. I hit escape, by the way, several times to stop Houdini to cook. And we want to do a random value of the detail. And what the random function does, as it does in Vex and HScript, it returns a value between 0 and 1. So if we hit enter, and now we move the display flag down to the for each, we get something interesting happening. We get some at 0 and some at 1. And even though this expression is returning a floating point value from 0 to 1, never reaching 0, never hitting 1, so we now know that this depth function does a random value on it. In other words, if it's 0.5 or below, it'll return 0. And if it's 0.5, 0.001 and above, it'll return a 1. Sometimes the parameter will do a floor as well, so we just end up with a 0. In this case, it's splitting it up the middle. So all we need to do is to expand this from 0 to 1 to go to 0 to 3. We just simply multiply it by 3. And that gives us our random variation from 0 to 3. And so that's our expression. So we know the for each is working. That is stamp functionality. Stamp functionality in a for each block. We do have to know about the iteration. In other words, the infrastructure itself is levied a bit more on the user to set things up. But then once it's set up, I'd argue that it's a lot easier to manage the expressions inside of this than it would be with copy stamping, because in copy stamping you'd have to go and turn on, and we do have now in tools or under view, I believe we can actually show dependency links for all nodes. We used to have to turn these on all the time to make sense of some really complex setups, but I'm going to turn off the dependency links. So that's there. We're now going. Performance, it's okay. There really is no difference in performance between doing copy stamping and this new way of working. But there is an opportunity to use compile blocks. And what is a compile block? It's new for Houdini 16. And what it allows us to do is, in this particular scenario, when we're using a copy to points, we have the opportunity for a compile block to do 2 things for us. First of all, save all the per node memory caching of all the nodes, because compile blocks allow you to, all the nodes inside of a compile block will work on the same geometry. And the second thing is, in this specific case with copy to points, it'll give us threading. So where there's a performance option. So I'm going to hit down tab and put down a compile block now. So tab compile block. And a compiled block entry actually adds 2 nodes for me. Compile begin and a compile end. Again, I'm going to take the compile in. And this time, I can actually not worry about the compile begin and just wire in the compile end. And when I just wire the compile end, see what happens. All the nodes that are dependent for this for each will now be included in the compile block. I don't have to worry about the compile begin at this point in time. As a matter of fact, let's just move it up there for now so it's out of the way. So what happens is here is that all the dependents or all the children of for each will now be enveloped inside of the compile end convex hull. But this guy out here, and there's a reason why I dragged this out. The compile block does not know about this iteration. And the reason why is because of the constraints that have been placed on compile blocks by design. For safety reasons in terms of threading and trying to avoid any blocking in the threads, we force you to declare all the expressions as before the compile block evaluates. So that means we have to work on static functions. The problem we have here is this dependency from this expression /iteration can be changed, and it can actually break threading in certain cases. So what we did is this very unique way of working inside of Houdini. And so let's take a deep breath and let's get this to go. So step one, we need to replace this expression here, /iteration, with a new method. And let's see what that is. We have to put a spare value down here, point it at this iteration, and then index that local spare expression into the depth. Use the gear for that. So any node inside of the compile block that's referencing any other node, we need to add a spare input. So this is also added for Houdini 16 on all operators. We press that, and if we hover over the spare input, we can see here that there's a tooltip. Refer to this in expression as -1, such as endpoints -1. We don't tell you why you need this, we just tell you how to reference this. So why you need this. We're going to grab the iteration node and drag and drop that onto the spare input. So that's step one. We can make it local as well if you want. So you can put in /iteration or leave it the full path. // means go up one directory outside of myself, inside of the whole network, and then find that node. And now we need to replace in that detail function that reference to that operator explicitly as it's said in that tooltip to -1. Now it works again. So now we have the compile block working with all the various iterations or all the various states of the subdivide sum. And we need to do one more thing though. On the for each block, selecting the for each block, we can see that there's a little option at the very bottom added, multi-thread when compiled. Enabling that will now thread this entire block. Now if you have, let's actually go Control-Alt-Delete, and let's fire up the task manager. And so we can take a look at more details, and then we can see how our CPUs are faring. We can actually take a look at the various options in here, take a look at the CPU performance, and you can see how it's behaving. But what we want to do is let's add a couple nulls because we're testing this out and we want to see the performance differences. And let's call this null for each block, for each out. And let's add another null, and let's call this compile out. Actually, out compile, as I like to call these things, and then out for each. So out for each. So we can play it. The one thing about a compile block is it'll only evaluate when this guy is, when the compile end block has the display flag on. Nothing's stopping you from marching your display flag through and seeing this tree evaluate. When we do this, we're just working in regular SOP workflow where each node is caching its input and it basically passes on the input to the next operator, which it caches its input. But as soon as we move the display flag to the compile block, only the part of the SOP that's used to process the geometry is used. So we're not evaluating the or the SOPs don't have to worry about managing the memory, caching it, and holding it, or we don't have to worry about evaluating its parameters because it's all done when we enter into the compile block. So all these nodes are doing is just working on the same geometry in turn. So you save a lot of memory. And we're also now threading. So let's have a look at that. So if I go to the scatter and I set this to a very large number, let's try 1,000. And so now I have 1,000. That's not enough. Let's set it to 10,000. Let's really make this thing work. And so now we've got 10,000 copies. Relatively fast. Remember, this null coming out of the for each will be roughly the same performance as a copy stamp. So let's put the display flag on that and let's wait. We can see the status bar on the bottom of Houdini saying it's processing all the points, and now it's evaluated. So that took a number of seconds. And now let's see how fast the compile block works. And it's done. So much faster. I mean, we could do some analyzing of the times, but I can tell you right now in this particular case, it's about 8 to 10 times faster using the compile than it is with the for each. So that is why copy stamp is sort of hitting the dustbin. And again, as I said before at the beginning, this little icon means it's a no-go with compile blocks. It'll basically, the compile block end will error out and it'll say I cannot compile this network because one node is not compile friendly, and so you get an erroring out. Now when I did the webinar, somebody asked whether I could actually add a font, and I fumbled that a bit, but it doesn't matter. Let's actually do that here. So we want to put a font label on top of every box. This is a lot of nodes, so let's knock this back down to 100. And let's add a font SOP. And with the font SOP, we let's drag and drop that in here. It's not going to be part of the compile block. Let's actually work with this outside. And we want to use the same expression. So let's be lazy. Let's go to our Boolean. And let's grab this expression, just the detail expression. Control C. And let's go to the font operator and put Control V in here. This is a string field. So in order to evaluate, as we saw way back with the attribute expression, we need to put quotes, some sort of quotes around this. In this case, back quotes to evaluate it. And if we press that, we can now see that we get an error because it doesn't know what to make of any of this. We could point this at the SOP, so let's do that. So inside of here, let's backspace out of this and let's put in quote // iteration. And now we should stop the error, but it only returns whatever cached state this was in. And remember, we changed it from 1,000 to 100, so its cache state is kept 1,000 or whatever it is, very large value, or 10,000. I'm sorry, which was 0 to 9,999. So it's not even valid. So we need to wrap this up in sort of inside of the compile block, and the easiest way I know that is to put down a merge operator, and let's put a merge after the box, and let's wire in the for each, the font operator. Now as soon as we do that, the font operator is now going to be considered a part of the compile block, and that's good enough for us. It doesn't really need to be part of the, we'll see what happens when we now add the correct reference to this. So as we saw before with, if we move our display flag down to the bottom of the for each now, let's not worry about the compile block yet. We can see that the font is working okay. So what we need to do now is add a spare parameter. So inside of here, Nagir again, add a spare input, scroll down to the bottom, drag and drop the iteration into the spare input, hover over the spare input. We can see that it says use -1 for this particular parameter, and that's exactly what we're going to do. Put in a -1 in there. And now you can see already it's being enveloped in both the for each and the compile. So now we know we're doing well. You also see that we have a purple reference that we indicate to you that you actually have succeeded in creating a proper detail reference into that operator. And now all we need to do is move this font up because it's being enveloped by the box, move it up. And now we actually have an iterator number for every box in our loop. So pretty straightforward. Now, the font swap isn't the fastest. At rendering the font per cycle is probably not the way I would do it. I would probably create an attribute with a string and then use a way of rendering text after the fact, or use even smarter would be to use a bind selector in the viewport. So basically use a visualizer, a viewport visualizer in the viewport to display that. But the question was asked, so here you go. I'm showing you now how to do that with the font operator as well. And following these steps will give you successful compiles. But let's see again the performance. So if I go to the scatter node, and again, let's up the noise here. Let's go up to 1,000. And the font swap does take some time to evaluate. And there you go. Probably as much as it takes to draw it as well. And again, let's take a look at the for each. It takes its time. And then let's do the compile. And the compile is almost instant compared to the for each. So the compile is very much faster than using the for each. So some of the benefits of using, so if we use the middle mouse on any one of these nodes, in order to evaluate the geometry, it will force that operator to cache its input, to cache its geometry. So moving the display flag back down to the compile or on the template. If you are working on this for each network, you're going to notice as you poke around these operators, they will cache their input. So if you take a look at the memory inside of Houdini, you're going to go, why doesn't the compile swap save me all the memory? And the answer is you can right mouse on any node and you can unload the geometry, or just close and open the scene. And the next time you do that, you're going to save all the memory. So that's a little introduction into compile blocks. So now what we want to do is take a look at some of the files that I included with the distribution. So let's go open, and I've got a hot link here. That takes me to the directory of files. Lots of files I've included. Let's take a look at compile blocks. And the one example I want to take a look at is the points and stars in the Forge compile block. And the reason why that one is pretty interesting is the fact that I kept the circle out of the compile block. I just wanted to keep it out of the compile block for whatever reasons, and then process it in a pretty unique way. The end result is the same. We have a compile block that's doing threading, and it's evaluating everything in turn. But the way that I've done the pulling of the points is pretty interesting. I've taken my circle, a primitive circle in this case. So if I middle mouse on that, you can see it's a primitive circle. Let's turn the spreadsheet off. As a matter of fact, we don't need to see it right now. And I do a compile begin, and the idea here is for each template point on the copy to points, we want to resample the circle. So this is abusing Houdini's primitive types to really good effect. So we have a primitive circle coming in, and then we use a resample. And we resample by edge, maximum segments, and this is where I put that sim expression in. And as we can see here, the same detail expression, iterating over -1, and the spare input is set to look at that metadata one. This time I happen to call the node metadata one, and we're picking up iteration, the first element of the iteration attribute, and doing a floor between 5 and 10. In other words, we're remapping the random function between 5 and 10, and then we're flooring that. So that means we just basically taking away all the trailing digits, and then we multiply by 2. So that gives us the number of segments. In other words, what we want to do here is multiplying by 2 means we want to skip every other point. And by doing that, we pass that into a scales to size. And that's how we're scaling the points. Another, twisting in the wind of how to do procedural stuff in Houdini. There is no right way, there is no wrong way. I'm just showing you a little bit of a different way. If you have to process the primitives coming in, we can do that. Now, in this particular example, we actually used 2 compile begins. Remember in the previous example, I had the compile floating in space. In this case, I wanted to formalize the inputs. Reason why? Because many times we're building tools, and tools need to work on geometry on disk or geometry that the user is going to feed into the system. So for that, you can use the compile begin stops to formalize what's input. Plus, you can actually have operators that are not compile friendly. For instance, the test geometry pighead in this particular case is not compile friendly by that badge that we render on the non-compilable badge that we put on that object. And again, you generate all the different options. Again, I use an attribute expression to just create the normals. I could use the normal SOP, but I use attribute expression as well. And you can see that I'm utilizing nice tooltips. So these files are fairly documented, plus with lots of notes for you guys to reference and to see the various steps that you have to do to work on this, and some of the reasons why we're doing things the way we are. So there you go. So formalizing the inputs, processing geometry in turn. Again, we can see very quickly where the reference expression is. So it's going to be in the resample points as we saw before. Another example I've included is one from Jeff Late from the beta forum, and it actually goes over some really cool options that you can have with a copy stamp. And it is beyond the scope of this seminar, but I thought I'd just show you a couple interesting features of it as well. So now with that loaded in, it's a typical Houdini example file that a lot of people ship with. You can see that we have lots of objects in here as examples. Yeah, it's a typical Houdini thing. So if you're coming for another application, you go, wow, aren't these supposed to be separate files? No, this is Houdini, and we can put as many examples as you want in here to cover over, in this case, from Jeff Late wanted to showcase the various different options. And if we dive inside the first one, this is an example that's pretty cool. Shows you two operators. And so it's an old-schooled operative chain of nodes. Each node caches its input, passes it on to the next. We can see that these two particular nodes are compile-friendly, by the way, but the Python node isn't. But what's really interesting is in this example, the Python node is actually used to call the operators within the Python script as verbs. You're going to hear a lot of this thing about verbs, SOP as verbs. There will be a master class on this coming sooner rather than later, but just for me to explain it, an operator, as I said before, there's really three parts to an operator. The first part is allocating and deallocating the memory, which we know is caching its input, and works on that input and caches the result of that and passes it on to the next operator. That's one part. The second part is the actual code that modifies the geometry. And the third part is parameter evaluation, UI stuff. And if you strip the two outside bits and all you're left with is just the actual code that's used to modify or create or modify the data, that is what we concern ourselves. And the whole verbification process is just going in there in C++ and making sure that your SOP adheres to the correct structure. And there you go. So you can call all SOPs that are compilable actually as actual calls. So you can say SOP node type category node verb subdivide, and you can set that to subverb, and then you can call subverb to modify the geometry. It's a really cool way of encapsulating SOPs at runtime in a Python script right from the shell. So you can actually encapsulate a lot of really cool Houdini workflow inside of Python, or Python as we call it. So if you have a Python shell, you have a Python function that calls operators like this, guess what's going to happen? And you pass in geometry, it'll evaluate the SOPs as verbs. Really cool example there. And a bunch of other inputs, parallel for each. Errors is an interesting one to see how errors are propagated. There's a whole bunch of examples in here you want to take a look at as to how errors get propagated and how you can inspect the various compile blocks to debug them. So that's also very important. So that's it for compile blocks for now. So we've taken a look at the copy SOP, copy to points, and the stamping behavior replaced with the new copy to points, as well as also have taken a look at the point SOP and how it's been deprecated and replaced. The third one we need to look at is the group operator. So let's take a look at some of the new options that we have available with regards to group. Let's start off with just a simple, let's do the pig head, so test geometry pig head. Hit enter and dive inside of the pig head, and let's go up one directory. So we're in SOPs. We can see it's non-compile friendly. I just like that there to see. We now want to work on some groups, and the whole thing about the group SOP is the replacement tab group. Just grab a selection, do group. And you'll notice that when we hit tab group, the old group SOP is gone. It is truly hidden. It is hidden from and is replaced with a whole bunch of various different group operators. Group and group by range are two of the key ones. Another one that we have is group combine. We can copy groups, we can create groups, and we can delete groups. Those are pretty, a couple of these were around in 15, but they've all been rejigged to be compile friendly. If I op on hide and put down the old group operator, you can see that it will not be compile friendly. As well, there's a couple really, one most oddest behavior of all with the group operators. It itself did not have the ability to work on a group. It didn't have a group parameter. So if I put down any modifier, let's put down a new point, SOP, you can see that it actually has an input group field. All modifier operators have this input group field, and the old group SOP didn't. The new one does, which is what this base group is all about. So I can actually write any expression I want in there and have that work on any group by name. So I can actually put qualifiers in there. Finally, we have a just simple base group parameter. And that's exactly what this base group parameter is. There's been a little bit of confusion as to what this is and how to use it. What it really is just any old SOP's group parameter in the way that it evaluates. So this isn't wrangling. This is the same group parameter options we have available to us in here to filter out groups. For instance, we could say here we only want to work on at p.y greater than 0, for instance, as a condition. And then if we wanted to change, it would only work on those point positions that were greater than y. So let's go back to the group, get rid of the point. And so now what we have is just a simple base group. We can do that. There are some shortcuts on here. And we can see that we can work on any incoming groups and process them. We can reselect by pressing that reselect button, hold down the shift key and select some more primitives. Lots of options that we've cleaned up in here as well. This is select fully contained geometry, select only what's visible, so I can deselect everything, and box selecting only see visible. We also added a new option, which is a window. So we can say select fully contained geometry only. So I like this option here, so you can actually only select what's contained inside the box. Many times you don't want to do a crossing, you want to do a window. So you might be familiar with that. That's now available to us as well. So front-facing window selection, yay! Wanted that for a long time. And so there you go, and you hit enter, and you've committed to that new selection. So that it works great for doing that, and we can say this, let's call this my selection. Works very well. So some other options that we have with the group, let's take a look at. So far we've been working on primitive groups. Alt drag this out a new copy, and now we can change the primitive selection to points. Let's get rid of this. And as I said before, you can type in here a great many expressions as you would in any group input parameter on any SOP. So in this case, by doing the points now, we open up the ability to use, for instance, at p. At p would not work with primitives or any other attribute because p is a point attribute. So let's do p.y is greater than 0. And now we're only selecting those points that are above the 0 plane. It adheres to the same funky business that we get in any input group SOP. If we put a space, it's invalid. It's really tight parsing on this particular input. But remember, again, this is just giving you, exposing you something missing in the old group SOP was I just want to p.y greater than 0 make a group without actually having to resort to writing an expression and doing vex wrangling. Really, really easy to get at that. So any attribute is fair game for the points here. Some things it cannot do is initialize normals like the wrangling does, cvex wrangling does. The normals actually have to exist prior to working on here, so it doesn't give you that automatic normal creation for you, but everything else is fair game inside of here. Let's take a look at a curvature example, for instance. So I'm going to alt-click drag this again and put down some curvature. So let's say we want to use a measure SOP and drag and drop that down there. And let's do curvature, just rename the node. And we want to evaluate the curvature. Definitely have to open up the spreadsheet on this guy. See if it's unpinned. I had it pinned previously, so it's unpinned. And in the curvature, if I middle mouse on this, we can see that curvature is a point attribute. Depending on what you're measuring, it can generate a different type of attribute. For instance, if we do area, that's a primitive attribute. So curvature is, or the measure SOP is one of those SOPs that will use a different attribute to write the data into. For instance, if we're doing area, there's area. And see, the minimum area is 0.03, maximum area is, or pardon me, the maximum area is very large, minimum area is almost 0, 5.087 to the minus 6, which is essentially 0. So might be useful in games to detect very, very small primitives and color them, although we have the polydoctor that does that anyway. So we want to get curvature. So the curvature is a point attribute, as we saw. Go to points and there's a curvature. Minimum value is, or the maximum value is 1,000. Minimum value is 0.03. We can threshold it as well, but let's leave all the values there. And so in this group operator here, we can now do something like at curvature is greater than, let's do 10. And now we can select those points that have a curvature greater than 10. And of course we can use the middle mouse button on here and we can slide this up and we can jig that. So middle mouse, you can middle mouse on any value, by the way, in any string inside of Houdini, and you can evaluate and use you can change the numbers as well. So you can see here very quickly the curvature that we're setting. 7 is good. And so that's really handy to know that the base group, we finally have the ability to access and write really quick parameter-like expressions that we would have on any other SOP. So the next thing we want to take a look at is some of the other options that we have available to us. So let's alt drag another copy of the group and do the input there. Let's actually add a dot so we get some nice links happening. And in this fourth group, we now want to turn off the base group. And that's another thing that really bothered me about the old group SOP, is we actually had folder tabs running along the top, and each one of these folder tabs was a different method. And the problem I always have is you put down a group SOP and you just want to select by normals and you forget to deselect the base group selection, and you end up getting selecting plus your normals, and but everything is right in front of you, and so we can actually take a look at the bounding regions. Straightforward. We have a nice bounding box, and it also works on bounding inputs as well. So pretty straightforward to select regions based on bounding box, bounding volume, and we have all the options available to us here, so there's no mystery there. Bounding sphere, bounding object, bounding volume. So if you're doing an old tutorial that uses the old group SOP and they want to bound by object, there you go. So let's alt drag that one, and let's do yet another selection on this. We want to turn that off, and let's do keep by normals. And we can backface from a camera, which is very handy. So let's add a camera in here. Control click. We added a camera, and let's jump back. So yeah, I navigate pretty quickly. If you're somewhat new to Houdini, yeah, I bumped around a bit. So I went from the camera view. Holding on the control key when I hit the camera tool actually gives the camera, and it inherits the current viewport in your window. Really handy. And then I just use the back jump arrow button to jump back to my previous location. So I'm just using those back buttons to jump around a bit if I'm going a bit too fast for you. So in this case, we now got a second group, and this time backface from a camera, and drag and drop. So this is another reason why I like this. And Build has this now too. Build now has hidden by default, by the way, is Control Z. Let's go back a bit here. It's hidden for you. And if I take a look here and I stow that, so in the Build desktop, you can actually just press on that to expand it. So you can do the drag and drop thing. I like drag and drop. Saves me from doing typos. And so backface from camera. And now we can see here the location of our camera. I have it on hide other objects, so let's say ghost other objects up here in the viewport. And now I can see wherever my camera, I'm selecting the back face. And let's say you want to have the inverse group. So what we can do, they used to have an invert toggle. Now we actually can put down another group operator. So let's type in group, and we actually have group combine. So again, the old group SOP had the ability to add and combine groups. Now we actually have a new dedicated operator. And let's call this first group backface. And it works on points. It also works on primitives. So if we want to select the backfacing primitives, we can do that as well. You can see they're in yellow. And if I move the display flag, it'll really be evident that they're backfaced. And then we can select the front face. So we can say, let's add a new group, front face. Is not equals all but backface. So now we have our two groups. So if I middle mouse on this operator, you can see we have 8 prim groups, back face and the front face are the two that I created, and the other ones we've inherited from the actual model itself. So group combine is also brand new, and it's and you can keep on adding more and more unions. For instance, we could say, for instance, let's do a subtraction, and we want to subtract that with the pig face. And for some reason now we're only selecting the eyes for this bizarre reason, but let me see if there's another group that, let's do the pig neck. And so now we've removed the neck polygons as well from that. So subtraction with pig neck. So we can actually compose front face with a lot of control with group combine. So the next example we want to take a look at is, let's drag and copy, let's alt drag another copy for the group. Move the display flag over, and in this case we want to turn, let's turn backface off, and take a look at some of the other options. Many times we want to select all the polygons that are facing within a particular direction, and let's do the one direction. So for all primitive normals that are facing up with a spread of 180, it's basically going to select every polygon in my geometry. So let's slide this down. You can see very quickly how we can isolate those faces from within a particular direction. So we can get it right down to 0.5. So basically all those primitives, and if I turn on the primitive normals, that's exactly what we're working against. You can see the primitive normals that are roughly aligned with the 0, 1, 0 axis with a spread angle of 5. Just give me those polygons and move forward. Very handy as well. Another option that we have inside of here is non-planar. So we can actually pick out those non-planar polys. And if we had to, actually, let me undo that because I want to keep let's leave that. So let's alt drag another copy. And let's do the work in there. And I'm going to turn backface from the camera off and non-planar, because many times, let's call these non-planar. Some old ancient engines still need to have non-planar quads. At least you can take a look at their model, do that, or you can follow up with a divide operator. And the divide operator by default will subdivide polygons, and let's do the non-planar. So now it's only triangulating those non-planar polygons. Turn on my primitive normals. So okay, so I want to step back a bit now and take a look at back at the base group, using that group type expression parameter and showing you the limitations of that particular parameter. So let's all click drag a new copy. Move the display flag. Let's turn all these options on. Go back to base group. We want to add some color. So let's put down a color operator and drag that on top. And let's set it to random. Constant random. So we just got some random colors. And they're going to be point colors. So in the group, let's change it to points. And as with all the group parameters, if we put in here at CD, let's say dat R for red is greater than 0.2. And that will fail. The reason why is because the only way you can access a vector inside of the group parameter is by using either index 0, 1, 2 or XYZ. As I said, this is a very limited way of working. So if you wanted to do 0, you get the red component, and now you've got a selection where the red is greater than 0.2. Let's increase the threshold to 0.5, and now you can see that. So again, that's one of the gotchas. So if you put RGB in here, it will fail. You can use 0, and you can also use X. It's just a legacy of the group. Again, let me put down let's put another operator again. Let's pick on point because I've been using that all the time. Again, there's no difference between this base group parameter as a group input field and any SOP's modifying SOP group parameter. It has the same limitations. Again, another thing, let's alt drag this guy out. Another thing that you're going to be tempted to do, because we can do it in Wrangle, is to put an actual expression in here. Let's say you want to use the luminance of CD, and you know there's a Vex function called luminance. you're going to be tempted to do this. So let's type this correctly, luminance. And you want to say the luminance of CD is greater than 0.5. You can't evaluate vex functions or hgrip functions, or vex functions, I'm sorry, inside the base group and have it evaluate correctly. It will error. It'll give you a warning. And the warning will say it has syntax error. It can't evaluate that. So for this, you'd probably use a group wrangle. And let's use a group wrangle. So we actually have, or probably a group expression. And group expression is what you want to use that for. So group expression is also quite new. And we can copy this parameter, Control C, and literally put a Control V in. So this is what you would use to do vex evaluation. And we want to do it on points. And so then the group you want to put in here is my points, for instance. And there you get the same thing. So group expression is what you want to use if you want to use something a little bit more beyond what this group is doing. As I said before, this is just a nice placeholder for using parameter-like expressions to do that. So those are a couple gotchas that are going to get you. We can promote groups as well. So there's a new operator to promote this group. For instance, many times we're working on points, we want to promote them to primitives. So you can actually use a group promote. So that's what that's all about. Many times you want to take a point group and expand it onto primitives. We can do that very easily. And the group we want to promote in this case is going to be my points. And we want to convert it to primitives. And if I middle mouse on this, you can see that my points is now a primitive group. If we want to change it to a new name, you can say my prims. And middle mouse on that, we can now see that we got my prims. So yeah, very straightforward. Again, replacing some of the functionality that we had bundled in that single group operator, now split apart. Again, all compile friendly, all ready to go. So the next thing I want to take a look at is a file that I've actually prepared. So again, going to open to my hotkey directory, and we want to take a look at group type SOPs. And I have a single file in here, group create examples. It covers what I did show you already, and it also goes a bit further into showing you some other examples that we have. A whole bunch of different examples in here. So if I dive inside, first of all, the group create. Again, I cover all the various options of doing group, including fail by CDG and CDR. We now know why that is. It's because it's a limitation of just the input parameter of every modifier SOP, which the group SOP is now properly inherited. And there's a luminance fail, which I talk about with some nice tool tips, group promote, as well as group by normal direction, group by point edge up. This one's interesting. So it's quite common now to just get some rubber twice, some selection, and then we can put down just a group create, just select some points with a group create, just bounding box. And then we can color those points. And then we can do a smooth on it. So the smooth actually has seen a lot of work inside of Houdini 15. In other words, it's curvature dominant. So if I do the strength and the filter quality, it'll actually trace across the curvature of the geometry. But the edge depth is pretty cool. So let's step back to that and to the group. We can actually, go over the group here. We can actually do an edge depth. So let's set the edge depth back to 0, which is my single point selection right there. So that's point group is 6602. So that's point number 6602. And then we can grow that expression outwards. And you can see how we can grow based on edge marching. We can now trivially select a whole bunch of different points. Really quickly, we're going to see there is, and of course, group merging. There's a nice example on that where we can take a whole bunch of points from some curves. And this is your typical fence. This is just one of the typical ways for doing a fence example. We have a curve. We want to turn it to a fence. We want to copy our pickets, right? So one branch, we can use facet node to remove inline points within a tolerance, an angle tolerance between those points. And then we can create a group called post at corners for those points. And we also have a new group transfer, which allows us to take an existing group, which is going to be, and then we can add that new point onto the existing posts. So basically we can take any group and merge it onto any existing detail. So here if we middle mouse on this, you can see that we have 8 points in the group posts. And over here, we have those 8 points in the group posts, but now we've transferred that group onto the base curves with all the other points on it. Very, very handy to know about. And then finally, we can do a union on the segments. So, that's also a noose. So basically, we can now create another group. And again, it's just using that Pythonic slice nomenclature that we added to the input group field several releases ago, where we can take all of our points and select every third one. And this works in any SOP's group input field that works on points or primitives. So we can use this slicing nomenclature from Python borrowed over with the :3. So that means we're selecting every third point. And we're adding that to posts. And so basically we also have this option in here under initial merge. We can replace existing. We now lose our corner points. Or we can say union with existing, and now we get back our corner points. And we just do a simple copy to points of a chariot, and we're off to the races. And it's your typical Houdini thing, where we can take our initial curve and you can move the points and you can see how you get your number. And of course, we've added a new option in Houdini. You now actually have to turn on the construction plane if you want to constrict your point. Or we could have just used if I would have hovered over that, and I could have used that nice handle as well to move the point around. So you can see here we got our automatic start at. How many different ways is there to do that? Many, but that's a really good example of using the group operator in that particular capacity. So let's go up, and next one we want to take a look at is group expression. And the group expression allows us to write an expression. So we started off with the squab, and we can now write all kinds. We saw the vex expression just a bit earlier, where you can now use any simple wrangling. Spaces are allowed, and you can now write some, you can incorporate vex functions inside of here, and it uses the same lmnum that we saw in the point SOP replacement, which is the attribute expression SOP as well. So the group expression is analogous to the attribute expression as well, in that we can use primitive points and the same expressions work in there. And we have all kinds of shortcuts in here that you can have a take a look at for taking a look. And of course, we can then do work on that, like such as a polyextrude, hit the escape key, do some really interesting stuff. Again, some other conditions with the rand, more expression examples. Rand, again, add lmnum works just fine to pick the element number that you wish to work on. And now you can very quickly add really cool random groups on the points, and then we can color those points as well. So quite a few examples on here. And here's another example of using curvature, 0 to 1,000. We can now use a group expression to that same curvature test. Again, much more lax. We can use spaces and simple, straightforward vex wrangling. Single line vex wrangle. We can't do multiple line wrangling. And let's say we want to copy some barnacles on that. So we want to do a curvature test, and the curvature is less than 10. And so that we can do a barnacle weight, we can add a group called barnacle weight. And then we can paint an attribute as well. And we're going to call that barnacle weight. We can just paint any attributes we want. So let's hit enter here. And I'm going to move my display flag down to yeah, I'm doing a lot of work down here. Let's move it down to the switch the barnacle method. So really what this example is all about is just how we can merge point groups together from attributes as well. So I can go to the barnacle weight paint here, and I can paint out or in any barnacles I want. And we can actually use attribute mapping onto groups with the group expression. So we can say group barnacles, we can say add barnacle weight greater than or equal to 0.75, which is what we're painting into, which is the barnacle weight attribute. And then from there, we do a whole bunch of things. We scatter the points and we copy spheres. So it's a really simple example of how you can use input groups as attributes, or attributes into input groups, and then you can scatter based on those primitives if you want. One of very many ways of working. Group by range. This is one where we're going to see, it's come up in the forums a few times where we can't do a trivial begin point, end point. But stepping back a bit, we can do really quickly group by range using the new group by range SOP to create a range of start and end. So we can create any pattern of inputs and outputs, and depending on the way in which the geometry was organized, you can have some pretty interesting results. Toruses can give you bands, for instance, the way it was constructed. And of course, these are all sort sensitive. So I'll show you that. So you can put a sort SOP in here, And you can sort the primitive order as well, so you can put a random primitive sort, and of course that's going to give you random results. Depends on the construction history of, or how the geometry was constructed. And Houdini's primitive operators tend to be very, very organized in the way they create the primitive numbers, as what you would expect. Another example here is that one thing that's challenging to do. So what I've done in this particular example is given you a way of easily selecting the beginning and the end point of a curve segment. And I'll show you the problem here. So let's scatter. We've got some points that we're scattering on a grid, and we're point wrangling those to set some pre-scale up, and then we just copy the line segments to those points. But you want to put the beginning point and the end point of the line segment in a group. We can do that with a group by range. But the group by range actually has a number of inputs and outputs as well. But this is arguably the one thing that is a lot harder to do in Houdini 16 than it is inside of 15. But I've given you a way out. You can save this as a preset. And then you can load this in whenever you want, if you want to use this way of doing it. So you can do group by range, select start, and we can use an endpoints op input path. So let me Alt E this. So when you use Alt E on an expression, it expands it up. And all this is doing is just basically taking for an endpoints function, just return to me the number of points in my input. And op input path is the modern way of expanding my input name, so you don't have to use .. and hard code the name of the input. You can use this expression. I do this all the time. And you can say calculate the number of inputs, number of points of op input path of me dot. Let me control it. Op input path, and the first is the path to op input path will expand a path to a node target. So I'm saying op input path of me, my first input. And that will return to me the name of the node that's wired into my first input. And I do -1 because we count from 0. 0 to n is -1 gives me the total, and that's what I'm doing there. So that gives me my endpoints. And then the root is pretty tricky. I just do a start and the end. The end I just set to the number of points -1. That gives me the root point. And for the endpoint, the tip gives me that as well. That also gave me the opportunity to use an attribute VOP. And this is a really cool technique for calculating or for doing finding endpoints. So in the attribute VOP, if I double click inside of this guy, let's make him a bit bigger. It's a nice little VOP network of how to use, even though this is iterating over points, we can return the vertex number. And so this is a simple VOP network that given the vertex number of the input for every point that's being processed. And if you have primitive that has 4 points on it, it's going to be vertex 0, 1, 2, 3. And so every point is going to have a vertex that's shared with a poly, so it rips through. And what this allows us to do in the line segments is to automate using some simple Boolean operations. So we can compare the vertex number. So if we say, okay, if the vertex number equals 0, you're going to be true. If not, be false. So if it's true, we then go to the roots, because we're assuming that the curve point 0 is going to be the root, or the vertex number of each line segment of 0 is going to be the root. And then we have, if we take the vertex number and compare it to the total number of vertices -1, because remember, the number of vertices was always going to be from 1 to n. And if we start counting at 0, we have to subtract 1 for our total to get the right value to march against. So we do subtract 1, and then we can compare. So if the vertex number is equal to the last vertex in our line segment, go to group tip. And then we do an OR over here. So this is a VOP for OR. So so if either of these conditions exists, go into endpoints. So there's a nice little thing. Make an asset out of it, and there you go. We'll see what happens moving forward. And there's your copy to points, and then you can zoom them out. And, arguably, this option has the ability to work on any curve anywhere within the SOP chain. So again, the example's there for you guys to have a look at. And that's it for a really brief look at the group operators. Now let's have a look at the Boolean SOP. New for Houdini 16, very exciting operator. I'm using it in 3 different ways. First of all, it's just the classic Boolean operations, union, subtract, etc. And the nice thing that I'm finding about the Boolean is you can have, on the one side, very dense small polygons, and on this side, very large sparse polygons, and it still holds together. And not only that, you can actually animate either one of the 2 inputs locations, and the Boolean just hangs together very well. The second option, the second way I'm using it is self-intersection cleanup of geometry. And that one's pretty interesting. Many times we need to have really clean manifold geometry going into our simulation tools, especially for creating volume sources or SDF collision geometry. So this is a big improvement with the Boolean operator. And the third one is for shattering geometry. Again, another new exciting use of Boolean that makes a lot of the shattering tools inside of Houdini pale in Houdini 15. And Houdini 16 actually has the shatter tool moved over to the new Boolean SOP. So let's have a look at Houdini. So fresh scene, let's put down some test geometry, in this case the rubber toy. And what makes the rubber toy a really good candidate for the new Boolean operator, we're going to be using it in the second mode that I talked about, where we want to take a piece of geometry that's comprised of multiple pieces and make it manifold. In other words, a single water type piece of geometry. What makes Flippy so non-conformant for doing volume creation and also doing SDF creation is the fact that it's comprised of a whole bunch of different pieces that are basically jammed together to typical jammed together model. So I can hit the escape key, hit enter again to get out of that state, the select state that is. And now, first thing we're going to do is, if I am bringing any geometry that we want to convert, let's take a look what happens if we just put, for instance, down a fluid source. And the fluid source is the node that a lot of our shelf tools put down for fluid simulations for doing collision geometry, sources and all of that. So we're going to go to the container settings and we're going to set the source smoke. We're going to change the initialize to collision and move the display flag down. We can see here, so far looks okay, but we're notice already there's some missing pieces. And as we decrease the division size, we'll notice that it's really not doing the best job. The assumption for generating the SDF geometry is that it's manifold. And we can see how it's failing on those individual pieces. Let's fix that. So the first thing we're going to do is, on the test geometry, we're going to insert, let's do a polyfill. Also a new SOP inside of Houdini 16. And what makes polyfill really cool is, again, I can just select my test geometry and select some, as we saw before, I'm basically going to select some primitives, and I'm just going to turn the connectivity off and select some geometry down in here. And I've got front facing on as well as window selection. And let's select another selection there, holding down the shift key to do add selections. And let's do some selections down there. And actually, let's select that, select something there, and select a couple primitives down there, and then blast those away. And we'll notice that the polyfill just fixes everything up again, bypassed, unbypassed. So that's the first thing you want to do. So if you're bringing a model from another piece of software, there might be some missing holes or some seams that are not quite tight, and you can use the polyfill to fill all those holes up. And this is classic Houdini. Notice how the polyfill tries to reconstruct the correct attributes associated with the geometry. And in this case, the UVs are fairly well there. You can see there's a slight artifact there, but for the most part, the attributes are kept intact and ready to go for simulation workflow. Again, the fluid source is still not going to see any benefit from that. So the next step we're going to do now is a Boolean operator. And the Boolean operator, when we put it down, it defaults to doing self-intersections. And you can see set A is what we're working on with the set A input. And we can see it's treated as solid. And when we set the operation to intersect, what it does is it does a loop for all the different pieces, and it does a self-intersection test. And we can see if it passes the selection test. If I just double click on all of this, or go select 3D connected geometry, and I select, let's select all the face, turn that off, and we can select some faces. We can see that we select everything or nothing, so we island 0. and it gets us everything. Oh, actually, I have to select the Boolean SOP, and I do that. You can see that we actually have the entire piece is now manifold. Yay. So hit escape and enter again to get rid of the select tool. And now our fluid source is doing very well. And so that's the first thing that we can do with the Boolean operators to clean up our geometry to create first-class collision geometry. The second thing we can do with the Boolean is let's do a simple test. We're going to have a box. And we're going to put down, again, I have create in context. Remember I set that. I'm going to do tab grid, and the grid's going to be added inside of the same object. And let's do a scatter operator on the grid. So I'm just going to put down a scatter node, and we're going to scatter some boxes. And so let's put down a box. Leave the box at unity scale. And let's do the scatter. Or pardon me, after the scatter, let's do a copy to points. Copy to points. And the left input, I'm going to put the box. And the right input, I'm going to put the scatter. And you can see that we have all the boxes intersecting. And in the scatter, let's do output attributes. Again, let's put out the output radius. But we want to modify the output radius. Let's actually use an attribute expression. And under the scale, we have p-scale. Remember the scatter SOP, if I middle mouse on it, it's generating a p-scale attribute from the output radius, p-scale. And the attribute expression, we're now using p-scale. And remember what we said before, we could do self, and there's a couple of really nice options in here. So we want to do multiply constant value, or multiply by constant value to self times value. And now we can make them so that they somewhat intersect. And there we go. And later on, what we can do is we can take this grid and make it larger. And as we make it larger, the boxes are going to try and envelop each other. So let's actually put a transform after the scatter. So what I want to do is scale the boxes apart. And let's take a look at the scale now, uniform scale. That's what I wanted. And so we can animate the boxes going out to in and pass that into the Boolean operator. And just to show you how robust this operator really is, so I can go to the attribute expression, I can go to the transform now, and we can now scale this down. And we can notice that the Boolean is simply doing all the self-intersection tests for all these boxes. And it's giving me a single manifold piece of geometry. But we can use the Boolean operator in several different modes. So this is actually manifold. Well, notice that the tops are all coincidence, doing a very, very good job. So in the Boolean operator, we can choose to intersect. We can also use a shatter option. And once we do the shatter option, it'll take all of the self-intersections, and instead of doing a union or subtraction, it actually keeps all the pieces, but it will recursively cut all of the geometry. And one really quick way to actually have a look at this is to use the explode operator, which is the exploded view. And we can then just quickly pass it into there. We can see all the various different pieces. So this makes for the most amazing greeble type tool. You can greeble anything on anything, and with the shatter tool you can actually keep all the pieces intact. So if we want to destroy the face of an object, for instance, that has all kinds of greeble on it, done with the shatter tool, you'll be rest assured that all those pieces are going to be unique and ready to go for any kind of destruction that we want. So really cool options. So let's save this file just to my desktop and call this H16. And now what we want to do is take a look at a couple other example files that I've created for the Boolean. So let's go File, Open. Let's go to my preset directory in here, and let's take a look at the Boolean SOP. And got a few of the options in here. Boolean Grid Cutter is a good example file that I put out there just to show you how you can take any geometry and start to build your own shatter toolkit. And down in here I have an exploded view of a shatter between a box that's being subdivided, and it's going to mount an operator on it. and of another object, which is just a whole bunch of grids that I just created and added some noise to. So a grid on a line, and I just merged them together to create some nice shatter planes. And then I run it through the Boolean tool. In this case, I actually have a manifold piece of geometry cutting by non-manifold geometry or just sheets or polygon surfaces, and we can see how set A is set to solid and set B is set to surface, and it just does what it's supposed to do. It just basically cuts your geometry up, and the operation is shatter. And then we run it through an assemble operator, and the assemble operator takes all of our objects and turns them into pieces. So we can see here under there's a name option in here, the name attribute, and each piece, if I middle mouse on it, is a packed primitive. So you can see packed fragments ready to go into the rigid body system. And then of course we have a poly bevel. If we wish to do any of this, any post work on it, we can absolutely do that as well. And on the other side, we actually have a bit of a different shatter, same setup. Okay, so there you go. Pretty straightforward. Another file that we can have a look at inside of here is, let's do cube self-intersection. Oh, we did that one, but let's take a look at Booleans deleted small pieces. And in this file, it's just another example of using shatter where we have a sphere, a grid with some normals copied to points. It's the same example, but this time we've done radiating grids. And the grids themselves are also self-intersecting. This can create some pretty nasty geometry, geometry that may or may not work in the Boolean simulation, but in bullet simulation, but still it gives you really cool fragmented types of geometry. And of course it's all resolution independent. I can go up here and increase or decrease the resolution of everything that I'm working on, and it does a great job. So that's a little look at the Boolean operator. Lots of examples. I mean, the more classic cases for Boolean just work very well as well. I'm just showing you a couple of the different options of Boolean that are a bit out of the box. So now I want to take a look at another new SOP, polypath. And polypath really replaces a SOP that we used to use a lot called the join SOP. And the join SOP allowed us to join different curves together. The only problem with that is the primitives had to be in the right order. So let's have a look at polypath. So what I'm going to do is use the curve tool, and I'm going to start drawing some curves. And so there's my first curve. I'm now going to dive inside of the node. And again, remember I have creating context set, or I'm going to set creating context on. Now I'm going to add a whole bunch of other curves. So tab curve, it should be on. There's tab curve. And I'm going to start drawing a curve from over here. And notice how my curves are all in space because I don't have that on. So let's turn that back on again. Hit enter. And actually, let's turn snap on then. And I want to start snapping from this point here. Or hit Q to repeat the command again. And I'm now going to start drawing another curve over here. And hit enter. And let's draw another curve from over here. So let's hit Q key to repeat the previous command, snap to that point. And I'm just going to start drawing a curve over here. So the trick here is that each curve has its own, it's all, they're sort of close to each other in the way that they connected their ends together, but they're completely different primitive order. So let's merge these all together. And so grab them and just drag and drop the one. Move the display effect to merge. And now let's put down a polypath. And the polypath is new for Houdini 16. We wire it up. And we can see here that connect endpoints. And then we can increase the maximum distance until they all snap together. And when they do snap together, I have a single curve. And let's turn off the selectable template flags and all the other nodes that we get when we do creating context. And if I middle mouse on this, you end up with a single primitive, a single polygon, all connected together. And this saves us a lot of headaches wrapping around tools around the old join SOP. So consider the join SOP gone as well. And And there you go. And next up are the two intersection type SOPs. We have the intersection analysis and intersection stitch. And for those, we're going to turn to, again, another couple files that I've prepared for you guys. So first of all, intersection analysis. I have a pretty interesting use of intersection analysis. Intersection analysis is very similar to surfsect, the old surfsect SOP for NURBS. It's our bent on trying to have polygon equivalents for all the NURBS type operators. So inside of this particular scene file, I have a whole bunch of different options of using intersection analysis. This is not the Boolean operator. It's its own unique code. So it performs quite quickly. So first example up, I have a tube and a sphere. Let's actually hide other objects. So we're just working on this, turn off the templates. And so here we have a grid, spacebar G to zoom in on it, and then a sphere. And we can use the point intersections. It really likes it if the input geometry are triangulated. It doesn't have to be, but in order to evaluate the attributes at the intersections accurately, it's probably best to triangulate all the geometry coming in. So for instance, if this was quads, we could always put down a divide SOP and force triangulation of our inputs. If we wanted to keep the grid intact, we could always triangulate, and then we don't get that warning on the point intersection in the intersection analysis. So what we're getting here is the intersection points, and let's select these two and let's do a template on them. And you can see here the points are actually forming around the, let's select this guy again, and we can see that the points are actually occurring where the sphere does intersect the grid. So really cool. We can also generate segments from that. So let's turn the templates off of those two guys, and you can see here that we're now generating the segments. It's got a warning on it, and it says a triangle and curve mesh is required in the input for correct attribute output. So again, let's just drag and drop that divide into there. And now we can see that instead of getting a row of points, we now have a nice curve. So this gives you a robust functionality for doing intersection analysis between any two surfaces, in this case a grid and a sphere. Some other examples of that. So we have the rubber toy, we triangulate the input and we now know why. We have a switch, so you can actually see, I have a switch in there so you can see whether or not you get the warning or not. So if you move the display flag onto there and you move the switch over, you can see you get warning, no warning. And as I said, it's all about doing accurate geometry testing, so that's what that's all about. So we can now see, again, Flippy's getting beaten up again. We can see now where all the various pieces are doing self-intersection. So if you wanted to see if the geometry was self-intersecting or if the pieces were self-intersecting, you can actually put down an intersection analysis. You can see here there's a couple points up there that are actually due to polygons that are self-intersecting. Yet another interrogation tool that we can, and again, I always hit accept and escape and enter to sort of clear that selection state. It's just something I do really quickly. The third example is pretty interesting as well, where I have a grid and I have a line and I do a copy to points. And we can actually cut against grids and lines as well. And in this case, I have a whole bunch of stat grids. And let's move that on. So a whole bunch of stack grids. And on the right side, I have a height field. And I add some height field noise and height field distort. And then I convert the height field to polygons. Now I can use the intersection analysis in a couple really intersection analysis of a single grid. And I could move that grid up and down, and I can test the intersection between all the different parts of that height field that's converted to polygons. Or I can take that grid of polygons and then cut the height field with that as well. And then we get contour lines. So it's a pretty cool way of generating really cool topographical contour lines from any height field, converting it to polygons or anything for that matter. So really, really interesting tool. I've just started to explore the possibilities of intersection analysis. These are a couple simple examples of using that tool. So the next one I want to take a look at. So intersection analysis is all about surface-surface intersections. Next one is about intersection stitch. So let's have a look at an example of that. And this one is really good at doing stitching-like operations. So here we have a box and a grid. And again, it likes to have triangles, so I have a little bit of munging up in here to ensure that we have triangles with the subdivide. And then we have another tube converted to triangles, again with the divide SOP, do a transform on it. And then here we can see that, so the intersection stitch is actually working on two surfaces. And if I go to the transform here, you can have some fun. If I hit the M key or the N key, or pardon me, go to here, select this guy, and hit the M key, I can move the position of the I can actually move the space of the handle, and I can move it so it sort of sticks out. And you see it does a pretty good job. Again, this is not the Boolean operator. It's simply just doing an intersection analysis test between two pieces of geometry, and it gives you the result is actually a geometric result. And it does a pretty good job of triangulating the geometry. You get some really long triangles. So the topology isn't maybe as good as what you get with Boolean, but still it's really fast. Another example is, let's take a look down here, is where we can do a self-intersection between lines and grids. So again, this tool works with just open lines. So we have a little bit of a network here. The result is using a copy to points as we just have just a grid of lines. And then we can use those lines to intersect against the grid. Again, that's done a mount. It's just gone through a basic turbulized with a mountain. And then we can intersect the curves with any terrain as well. So if we need to give some curves a haircut by any other piece of geometry, we can do that. So this replaces the curve sect like functionality that you get with NURBS curves or any open face on a NURBS surface. So, and of course you can extract just the points where the intersection happens. So another example of intersection stitch, we have a curve, and we can take that curve, and on the other hand we have a whole bunch of other curves, and we can do curve cutting. So curve sect, again, exploring those options that you get with the curve sect. And I can actually go to the select tool, and you can see here all the various pieces that we have. So if I select 3D connected geometry, you can see here, or actually not do that, let's just select geometry groups. And you can see that we have all these different groups, and if you select them all, you can see they're all individual curves. Very similar to the workflow we get with curve sect. But this tool actually does a little bit better than curve sect. It actually does curve and surface intersection as well. So two very, very useful tools for building procedural systems. The last SOP I want to look at today is the attribute blur SOP. Let's go File, New. Actually, we're going to open up an existing file. So Open. And down here I have an attribute blur SOP, not in a folder, like it's an example, so let's open that up. And the nice thing about attribute blur is that it can actually it's a brand new operator, very, very powerful operator. Let's hit escape and enter to get out of that select state. And so we start off with the squab. And the squab has a whole bunch of attributes on it, so I'm going to use an attribute delete to blow away all the primitive and detail attributes. Again, it should be common, just a middle mouse to see what attributes I have there. And then the attribute delete, they're gone, except I keep the vertex UVs. Why not? And attribute create allows me, so I'm going to create a new attribute called myAttrib. And the reason why is I want to paint into that attribute. And then I purposely am painting on the insides of these tentacles, and what I want to see is whether or not the attribute blur can actually blur based on topology, because that's a new option available to it. So I'm going to actually paint a little bit more inside of here, Control-C, and zoom in on here and paint down in here, and I'm going to see, and let's middle mouse out of that, let's get rid of that, and I want to see how far I can make this attribute crawl across the surface as we increase the various values. And let's go down in here, add a bit more paint. And so if we, in previous version of Houdini, we actually had an positional based blur. So what would happen is if I had a point down in here, this point would blur onto that given enough distance. But let's have a look at what the attribute blur does. So the attribute blur will take that attribute and blur it. We can't see it, so we actually use an attribute visualize. So the visualize operator actually is visualizing. If I go to the visualizers, we can see that the attribute I'm blurring is myAttrib, which is being created up here with the attribute create. Actually, let's call this myAttrib. And then we paint. Let's actually go let's abuse the fact that the name of the operator is a paint into my attrib. So we're actually painting into that attribute here, my attrib, overriding the color with my attrib, and then the attribute blur. And then we have to use the visualize to actually see its effects. So the attribute blur has a method to do uniform or edge length, which is the way it crawls across the surface. You can try the two. Let's try uniform or edge length. So basically one is biased to the length of the edges, and the other one is just uniformly blending across the edge. It doesn't care whether one edge is shorter or longer. It'll just uniformly blend. So you'll find that this one will spread a little bit more evenly, where the other one's going to crawl along the edge length. And then we have blurring iterations, which controls the number of iterations that we're going to be blurring recursively over. And you can see as I increase that, we're actually blurring across the surface, and we're not actually getting any of that proximity type blurring. So pretty neat. And as I said, the influence type down here is what determines its behavior. So we have connectivity. We also have the older proximity version. So now you can see that, yeah, we're getting cross bleed across the tentacles based on proximity, not crawling across surface connectivity. So this will allow us to now bleed attributes into areas that we would normally not get by just doing simple proximity scattering, where you just get locality determining it. So really useful operator for pushing an attribute across the surface. And of course, the more blurring iterations we get, the more that we blur that attribute across the surface. Let me turn off some of those advanced shading. Let's just go to the constant shading here and turn that off so you can actually have a look at what it's doing. And let's get rid of let's just actually take a look at smooth shaded itself so we can just see that crawl across. Really cool operator. Again, you can do all kinds of games. You can do two visualizes, subtract the two with different values, subtract the true, and get a leading gradient edge by linking the two together. I mean, the number of options you have with this operator are pretty much endless for crawling attributes across the surface. And of course, if you need to take my attribute and boost it up, just like you would do in compositing, let's now go back to the attribute expression. No need to use a wrangler to do the really basic stuff. So attribute expression, what I'm going to do here is I'm picking on custom attribute, and it's my attrib. So actually I could actually, yeah, my attrib, actually under the name, it should be my attrib, and it's a float type. And now I can actually go to the expression, and I can do we can do a multiply by constant value. And so we can actually increase or decrease the brightness as we go. And now that we have the visualize with an attribute expression going, nothing's stopping us from adding yet another attribute blur. So if we select the attribute blur, alt-click a copy and wire that down and move the display flag to this attribute blur, we can now see that we can expand that even further. So bringing compositing-like techniques into SOPs has always been a time-honored Houdini tradition. So if you're new to Houdini, there you go. You can bring your compositing-like chops into Houdini and constantly do more blurring iterations on here. And you can do as many iterations of attribute blur as you want to crawl an attribute across the surface. And of course, we can boost this attribute as we always do in compositing, make it very bright. And at the very end, we can use yet another attribute expression or an attribute wrangle to clamp that attribute back down to values. And this time, let's put down an attribute wrangle because I want to use an actually, let's use attribute expression. Why not? And let's alt drag a copy and wire that up into there with the display flag to the attribute expression. And what we can do is we don't even, so the attribute we want to do custom my attribute, and what we want to do is clamp self. So we can actually put in down here clamp self, and we want to clamp it between 0 and 1. Hit enter, and there you go. And we can verify that in the spreadsheet. If we go to the spreadsheet, we can see that my attribute is varying between 0 and 1. And that concludes the very long look at a lot of the Houdini 16 operators. There's an awful lot more that I'd like to cover in the future, but for now, those are a few of the more exciting operators that I'm enjoying very much inside of Houdini 16. I hope you had, I hope you learned a bit, and hopefully moving forward, there's going to be an awful lot more improvements being made as we go along. But Houdini 16 for me is a very exciting release, and I am using it a lot differently than I have been using previous releases for all the reasons that we've been talking about over the last couple hours. Thank you very much for your patience, and until next time, bye.